This is the quiz for Unit 6. So with number 1 here, it says we want to write the fourth root of x to the ninth power using rational exponents. Remember, for a rational exponent, we got to turn this thing into a fraction. So the way it works is our big thing down here. So usually we put a number down here, but we have x. So x is our normal thing. So our normal piece here, we're just going to keep that one as is. So we're going to just write a big x. Now 9 is going to be our exponent, so we need to keep that as our exponent. But when we do a rational exponent, we always got to make a fraction, and the thing that goes on the bottom of the fraction is going to be our index. Our little number in there is going to come down here, and we get 4 right there. And that's it. So we get x to the 9/4. So that's our value. So that's what we get for using a rational exponent. So again, we're not really doing much. We're just converting from our radical form to our exponent form. For number 2, we've got this formula. It says it relates the surface area in square units of a cube to the volume v in cubic units. What's the volume in cubic units of a cube with surface area of 24 inches? So we can see it tells us that A is the surface area. And down here it tells us the surface area is 24. So we'll put 24 in for A. 6 makes sense. That's a 6. V is the volume. So that's what we're trying to figure out. So we'll leave V as V. So we got V to the 2/3 power. So our goal is to try and get V by itself or to try and solve this equation. So what we're going to do is, I think we're just going to divide by 6 here. So that'll cancel those 6's out. So we get 4 equals V to the 2/3 power. Now, if we want to get rid of 2/3 power, we can just multiply by the reciprocal power, because power to a power means we're going to multiply. So we'll do 4 to the 3/2 power, because 2/3 times 3/2, remember that's going to be just 1. So those basically cancel out. So we're going to be left with V. So we have to figure out 4 to the 3/2 power. So I can do this because I can kind of remember 3/2 power means that's the square root of 4, which is 2. And then to the third power, 2 times 2 is 4, times another 2 is 8. So I can kind of figure that one out in my head. Now you might want to use this use your graphing calculator. So we could do that to figure out this 4 to the 3/2. So let's go ahead and pop that in. So right now we can type in 4. I'm going to use the little to the power of. So you want to use the A to the B. That way you don't have to delete the 2. So it's the power of 3/2, and we can see we do get 8. So that makes sense. So if you want to use the calculator to double check the calculation, that's what you would do. If you want to use the graphing calculator, we do have this formula here. And we said if we want to set this equal to a number, we can say y equals 24. So we always have to do y equals the number part. And then we got to put in our equation part. So that's 6v to the 2/3. So 6. Now x is kind of what we're solving for. So I'm going to put in x to the 2/3 power. And that's kind of a fun looking equation. Now we don't see the red line. We don't see the y equals 24. But again, we're only over here at like 4, 5, or 6. So we're going to have to zoom out. Now remember, in this section, zooming out is probably not good because it'll scrunch your graph up. We probably just want to go really far into the y's. So I'm going to come over here and I'm going to put in 10. I still don't see the red because I need to get up to 24. So I'm just going to add an extra 0. So if I don't see anything, I'll just add an extra 0. All right, so I see my red line. So that's what my graph looks like. It looks like I got 2 answers. So I got 8. I also have this -8 over here. But if we think about the context of the problem says we're trying to find a volume. If we remember from last year, a volume is a real quantity. We can't really have a negative volume for a cube. So what we would do is we would ignore our negative value. So we don't want the -8. We do want the 8. But remember, when we pick our answer, we don't take the 24. We don't take the y value because there's no y's effectively in our equation. We're not solving for y. We're only solving for x. So that's how we can get that with the graphing calculator, as long as you remember what to do. So that's what we get. So we get our value of 8. We see 8's right there. All right, for 3, we need to solve this equation. If we want to solve it by hand, we're going to use our exponent rule. So I see I'm multiplying. So the exponent rule we want to use is if we're multiplying with the same base, so these are both 5, we're allowed to add up our exponents. So x to the 3 plus x to the 4th, and then we get 5 to the 21st power. Now, like we said last year, if the bases are the same, the exponents have to be the same for an equation to be true. So since these are the same, we're going to basically cross those out and do x over 3 plus x over 4 equals 21. Now, a majority of people said they didn't like the fractions, so that's fine. So we have to pick a denominator to multiply by. I could multiply by 4, so usually we would just multiply by the bigger one. In this case, I'm going to be a little fancy. I'm going to multiply everything by 3. The reason is, if I were to do 4 divided by 3, I wouldn't get a nice number. But if I do 3 times a fourth, oops, I want to cancel that out. So 3 times x over 3 is x. 3 divided by 4 is 0.75. So I like 0.75 as a number. 4 divided by 3 would give me 1.3 repeating. I don't really want that as a number. And then 21 times 3 is 63. So we're just solving for x. We'll combine our like terms. So 1.75x equals 63. So we combined our like terms. Here we're going to divide both sides by 1.75. And I don't really know 63 divided by 1.75, so I'm going to use my calculator to figure that out. So 63 over 1.75 gives me 36. So I get my answer. That's kind of nice that one came out nice. They don't always come out nice. This one did. Now that's if I want to solve it by hand. And that one, that's kind of in our wheelhouse. So most of us should be able to solve that one by hand if we want. Some people in class said they'd rather solve it with a graph, and that's fine. So we can solve it with a graph. So we get 5 to the x over 3. So put that in right here. To the power of x over 3. I gotta be careful here. Times 5 to the power of x over 4. Okay, so that looks good because the little numbers look like they're supposed to be little exponents up there. The big bases look like they're big numbers, so that's nice. And this one we had 5 to the power of, I forget, 21. I don't forget. I see 63 down there. Now again, we have to make it a number. Since it's a number, we got to do y equals. So I'm going to start at home, and I'm going to see, okay, I see the red line. I don't see the blue line. That's a really big number. So it's going to take me a while if I do want to zoom out. So I'm going to use the same idea. I'm going to come over here and use the wrench and switch this to 10. And I'm going to keep adding a few zeros until I can actually see that blue line. So it's okay that the red line went off screen, but we're pretty high up. To the 12th, to the 13th, the 14th, there's my blue line. So I see my blue line. My red line, you can't see it, but it's way down here. So what I'm going to do is I'm going to have to scroll to find out where I'm at. Could be positive, could be negative. So now is where I think I'll try the zoom out button. Still don't see anything. I'll zoom out again. And I finally see it. It's all the way over here. That took forever. Because again, this is a number that's times 10 to the 14th power. This is a really big number because we said these numbers get really big really fast. But they do connect. They do eventually connect. We do find our intersection. And so for our intersection, for all of our trouble, we forgot the answer. And look, our answer matches. Oops, the blue. We get 36. We get 36. So we actually do get the same answer. Remember the y, we don't use the y. The y we don't care about. That's not important for this question. There are no y's in this question. We just care about the x value. So if you want to use your graph, again, it does take a little bit of time to do the graph because you did have to kind of use the window correctly, but you can do it with the graph. All right, so then we move on to 4. 4 is very similar. We have to use our exponent rules to solve it by hand. In this case, these are not both the same, so we have to turn them into the same number. Luckily, 9 is just 3 times 3, so that's 3 to the 2nd power. So I'm going to transform 9 into 3 squared to the x plus 5 power. Then I have 3 to the 3x minus 17 power. Now I can't cancel out the 3's because this is still 3 to the 2, but we have our other exponent rule that says power to a power means we're allowed to multiply. So we get 3 to the 2x plus 10 equals 3 to the 3x minus 17. And now I'm allowed to cancel out those 3's since those are the same. All right, so I'm left with 2x plus 10 equals 3x minus 17. I think I'm going to move the x's over here to keep the x's positive. So 10 equals x minus 17. I think I'm going to add 17 to both sides because I have to get x by itself. And I'm done. I got 27 equals x. Now, could we do this one with the graph? Sure, we can do this one with the graph. We're going to have to do the same thing that we did with the last one, though. So 9 to the x plus 5. Oh, look, you see it doesn't work. We have to remember if we're typing it in, if we're going to do any pluses or minuses, we got to make sure we use the parentheses. Is that even right? 9 to the x plus 5. Yep. 3 to the 3x minus 17. So 3 to the power of parentheses 3x minus 17. All right, so I got to go back home because, again, I'm zoomed way out. So these numbers, again, to the 15th power, so you have to think 15 zeros. I see both of them, so that's good, but I don't know where they're going to intersect yet. So let's zoom out a bit, and we're going to zoom out again using our wrench. So we're going to start with 10. I don't see them connect. I'm going to add an extra 0. Sorry, computer froze. So add an extra 0, add another extra 0, another extra 0, still don't connect, still don't connect, still don't connect, still don't connect, still don't connect. Now here I got a little bit of a problem because I don't see the blue line anymore. So I'm going to zoom out so I see the blue line. Oops, I just messed up. Now I got to start over. 1, 2, 3, 4, 5, 6. All right, so we got there. So we're going to zoom out. So I still don't see them connect. So let's add some more zeros. I still don't see them connect. Still don't see them connect. Oh, they're getting pretty close. Oh, I thought I saw them connect. They did connect right there. What a pain. But they do connect. So we can zoom in a couple times to get a good view of it. See right there. That's where the crossover happens, and it does happen at 27. All right, so I thought that 10 to the 15th was big, but now we're at 10 to the 30th power. So again, it does take a lot of searching, but it does work. And if we look, we do get our value. Oops. It's right there, 27, 27. Don't need the y value. But just in case we were curious, this is 3 times 10 to the 30th. So that would be a 3 and then 30 zeros after it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So this is what this number is that it finally connects at, which again, kind of goes with the whole theme of the unit that these numbers get really big really fast. We only went 27 steps, but we're already all the way up here. So we got our thousands, millions, billions, trillions, quadrillion, quintillion, septillion, sextillion, septillion, octillion, nonillion. So 3 nonillion. So around the nonillions is when our number actually shows up. But again, we don't care about this number. We want the x value. All right, for 5, we have to figure out which one is exponential. We're going to pick all that apply. So remember, for exponential, the goal is to find the ones that are constant multiplication. Division is okay too, because remember, division is just the inverse of multiplication. So if I try to multiply, right away I can see a doesn't work because there's no way to multiply 0 to get to 1. So a is just completely off. All right, so for this one, it looks like to get from 7 to 7 over 3, I'm dividing by 3. Then to get from 7/3 to 7/9, I divide by 3 again. And then I'm going to divide by 3 again to get to 7/27, and then divide by 3 again to get to 7/81. Now again, traditionally, we wouldn't say divide by 3. Traditionally, we would say times 1/3 because we want it to be repeated multiplication. But again, if you want to think of that as divide by 3, that's okay. All right. If we couldn't see that, that's okay. What we would have to do is we would have to double check. To double check, we would do 7 over 81 divided by 7 over 27. And if we were to simplify this, the 7s would cancel. So we'd have 1 over 81 divided by 1 over 27, which is 1 over 81 times 27 over 1, which is 1/3. So we get a third. Now we need to check to make sure all of the others do the same thing. 7 over 27 over 7 over 9. 7's cancel, so we get 1/27 divided by 1/9, which is 1/27 times 9 over 1, which is 1/3. Then we'd have to check the next one. So we have to check all of them to make sure that they're all the same. So we got 7/9 over 7/3. So again, if we check it, we would get rid of the 7s. So we'd have 1/9 divided by 1/3. So 1/9 times 3 over 1 is 1/3. Then we'd have to check the last one. 7 over 3 divided by 7. The 7s cancel. So we get 1/3 divided by 1, which is just 1/3. So that one does work. Takes a little bit of effort to get C, but C does work. For B, it looks like B is going to work too. So we got times 2, times 2, times 2, and times 2. And you got to check all of them. So like 3 of them could work out, and the last one might fail. So you have to make sure that they all are the same. So B is going to be good. Again, if we weren't sure what we were multiplying by, we would just check by dividing the two that are next to each other. 80 over 40 is 2. 40 over 20 is 2. 20 over 10 is 2. 10 over 5 is 2. So those all work out. For this one, we can see it's going down by 0.1 every time, but this is not adding or subtracting. This looks like it's minus 0.1 every time. So that looks like it's not right. But to double check, we're going to do the same thing we did. We're going to have to do 7.8 divided by 7.9. That one I'm not quite sure on, so let's see what we get. So we get 0.987. All right. Then I got to check the next set. So I got to do 7.9 divided by 8. And if this one we should pick it, it would be the same, but those two things are different. So again, we see we get different decimals. So since those are not equal, there is not a common ratio, we would not pick this one. So we would not pick D. So the answers here are going to be C and B. B and C do work out. All right, for 6, we got to find all of our key features. So first we got to get the y-intercept. So the y-intercept would be the same thing as our a value, but this is the same thing as if it was 1. Oops, not like that. 1 times 6 to the x power. So our y-intercept here is 1. The asymptote is where we get to but never touch. So we're going to get really close but never touch. Now the cool thing is, since we've only kind of looked at our base cases, our asymptote's going to always be at 0. So we're going to say it's y equals 0. Our domain, so domain is always all real numbers for exponentials. Every single time it's the same answer. And then for our range, we would actually take our asymptote, and our asymptote is going to be either our lowest or our highest value. But we're going to go all the way up to infinity. Now, I should probably double check all these with the graph. So I'm going to graph 6 to the x power. So we'll do 6 to the x power. I'm going to get rid of the blue line. And I'm going to go back home. And we can see, yeah, we're getting pretty close to 0, but we're not touching. So if I want to double check that answer, I'd type in y equals 0. Use a different color. And we see that, yeah, that's the asymptote because the red line is getting close to the green line. But you can see there's no intersection over here. There's no like gray dot for the red and the green lines. So that's our asymptote. Our domain goes all the way to the left, all the way to the right, and it's going to start at 0 in terms of y, and then it's going to shoot up out to infinity. There's our y-intercept there at 1. Let me put the asymptote back in. I'm going to even make the asymptote look pretty nice. This little dashed line. Oops, not yet. And so there we go. So we have the graph to prove all of our answers. So if we wanted to use the graph to double check our answers, we can. Get a little bit smaller. There we go. So in this case, we do want the y value because it does say the y-intercept. So again, the y-intercept right here is 1. Our asymptote, again, this green line is our asymptote. I guess that goes all the way across. Domain is always all real numbers. And for our range, we're going to go from our asymptote at 0 up to infinity. So that's how that works out. All right, for 7, we have to graph f of x equals 2 to the x and its asymptote. So again, if we're going to graph our 2 to the x, our asymptote's just going to be hanging out at y equals 0. So I'm just going to throw the asymptote in right now. And if I'm going to graph 2 to the x, I'm just going to go ahead and pick some points. So if I tried some things out, I would start with 2 to the 0 power, because anything to the 0 power is 1. I got to be careful here, because again, when we do these exponentials, we're going to go up really fast. So it's typical for the graph to not be by 1s. So 1 would be about there. So if x equals 0, y equals 1, then we have to try maybe 1. So 2 to the first is 2. So if x equals 1, y equals 2. Then I'll try 2 to the second to get 4. So if x equals 2, y equals 4. So now we're right on this line. Then I would try 2 to the third. So I get 8. So if x equals 3, y equals 8. So come up here to 8. And if I try 2 to the fourth, I'll get 16. So if x equals 4, y equals 16. So that's right there. If I did 2 to the fifth, I'd get times 2 again to get 32. So if x equals 5, y equals 32. And I feel like I've got all the pieces I need for this graph because I know where the asymptote is. I can kind of see the curve going. So I've got the curve. So I think I'm ready to graph. I could put in some negative values just to double check. But I'm feeling pretty confident that this is going to go look like this. And we're going to kind of trail along but never cross the asymptote. So that's going to go forever in that direction, and that'll shoot up eventually. Now again, this is another good one we can double check. Sorry, I put all the y's here, but it is f of x, same as y. But we get 2 to the x. So again, we'll graph 2 to the power of x. And we can see that, yeah, I've got 0, 1. If I stay on the graph, if I go to 1, there's 1, 2. There's 2, 4. Right. It's close. I see it right there, 2, 4. Or if you hit the little gear, you can just make a little table and it'll plot all those little dots for you. If you want some more dots, we can do the ones we did, 3, 4, and 5. We can zoom out a little bit and see all those dots. Again, zooming out makes it kind of squished, so it's not the best to zoom out. Best to use our wrench to just change this to a 10 and then see 100, and then we can see the curve really nice. So that looks really good. All right. All right, I don't need this. I feel good with my graph. We already made the graph. All right, for 8, we need to get the function rule for the table. So again, we can use our f of x or our y, whichever one you'd like. So f of x equals a times b to the x power. So a is our y-intercept. We see here we're starting at 60. So we get 60. B is what we're multiplying by every time. So if I see this, I might see divide by 3, but we have to remember that's multiplied by 1/3. So if you see the division, you can always just do 1 over that number. And that's it. If you did not see that we were dividing by 3, or if you didn't know, you take the 2 that are next to each other, and we would divide. 20 divided by 60. It's always the second one divided by the first one. We can simplify that to 1/3, and we get the same answer. If I didn't want to pick those two, again, I could pick these two all the way over here. 20 over 27 divided by 20 over 9. 20's cancel, so we have 1/27 divided by 1/9, which is 1/27 times 9 over 1. And then this would cancel to 1/3. So we simplify down to 1/3. And that's it for number 8. Let me box my answer. That's what the answer is. All right, for 9, we need to get an exponential function that models this population. So again, our exponential function is going to be either y or f of x equals a. Oops, wrong color. A times b to the x. Well, a is how much we start with. That's our y-intercept. So we're going to start with 250 reindeer, so 250. And then b is what we're multiplying by. So in this case, we see we're decreasing at a rate of 15% per year. So when we're decreasing, we're going to do 1 minus. 15%, again, that would be 0.15. If you forget how to do 15%, just divide that percent by 100. And that gives you the decimal that you need. Sorry, that should be an x. And then x stays as x. And that's it. So it's a pretty quick one. So just kind of make sure that you're not putting 15 in here, but you're doing 0.15 for the division. Again, don't just put point and then the number, because again, 2% is not 0.2, that'd be 20%. So that's what we got. For 10, very similar. So we have to do an exponential function. So f of x equals a times b to the x power. Very good. Then we need to plug everything in. So again, our starting value, we're buying it for 6,000. And then this time we have to look to see if we're increasing or decreasing. So again, it's decreasing. So we're going to do 100% minus. And then our rate, we're decreasing by 10%. So again, 0.10. So 10 over 100 is 0.10 or 0.1 if you'd rather just do 0.1 to the x power. That's our answer for that part. Part B, we have to figure out how much it's worth after 5 years. We're just going to plug 5 in for x. So we get 6,000 times 1 minus 0.10 to the 5th power. Now, again, I don't know that one. I'm going to use the calculator to figure that out. Get rid of this. And that one. And that one. And that one. All right, so we got 6,000, 1 minus 0.1 to the 5th power. All right, so I get 3542.94. Now that makes sense as a final answer. You might think, should I round? Should I not round? So in this case, we have to remember what we're dealing with money. So, I mean, dollars and cents seems to be okay. So, this answer just as its own is pretty good. So I'm just going to report that. $3,542.94. If you round that up to $3,543, that might also be okay, because in the context, again, we're thinking about a company. Maybe they want a good estimate, so maybe the 6 cents doesn't really matter too much. But the official answer would be $3,542.94. All right, for 11, we have to compare these two options. So if we look, the two principals are the same. The annual interest is the same. The compounded is different, so those are not the same, but the number of years is the same. So for part A, which one's worth more after 5 years? We're just looking at our compounded, and we have to remember which compounding makes us more money. So we said in class that the one that is more compounded, the more often you're compounding, the more money you're going to make. So daily is 365 times a year. Monthly is only 12 times a year. So Sunbank wins because 365 is bigger than 12. So we're going to compound more. Then we have to actually figure it out. So we have to figure out how much it'll be after 5 years. We got to use the big equation. So our amount is equal to our principal. Again, that's just our starting amount though. So I'm going to switch that and put that back in blue because that's our starting amount. Oops. And since we're accruing interest, we're making money. So we're going to have our parentheses. But since we're gaining interest, we're going to do 1 plus because we want to have 100% plus some extra money. Now, our percentage this time is going to be 4%. Not quite there yet. Still writing the equation down. Our rate divided by the number of times that we have to compound per year times x, or times t, I guess, in this case. Since we're dealing with time and years, we'll make that the official t. All right, so what we got to do is we got to start plugging everything in. So our principal right here we see is $12,000. One is just going to stay as 1. And now our rate now is where we're going to plug in our 4%. So again, 4%, we don't put 4, we don't put 0.4 because 4 divided by 100 is 0.04. So we want 0.04. N is our daily value, so N is going to be 365. And then up here, I'm going to do 365 times T. Again, the only reason I'm putting this in parentheses is basically for Desmos because I got to figure it out kind of in Desmos. Oh, we don't T. Never mind. Even better. We got 5 years. So we can plug that in. Again, I'm putting that in for Desmos. Again, that just helps me keep track to make sure I don't accidentally do like a ×5 down at the bottom. So that way I'm making sure that it stays up top in the exponent. So we're just going to plug this in and we're going to get our answer. So nothing too crazy with this. So instead of 6,000, we've got 12,000. Instead of 1 minus, we've got 1 plus. Instead of 0.1, we've got 0.04 divided by 365. And up here, we've got 365 times 5. And that gives us our final result. So we're already done. At least we think we're done. But that answer isn't as nice as it was last time. So if we look at this answer now, we see this is not in dollars and cents, and we want to report an answer in dollars and cents. So we would want to round this. So 14,656.67. That's our final answer. Now this time the dollars and cents do matter because again, we're not making an estimate for a company. We're actually finding out how much money we have. So we want to be very specific so that we know how much money the bank actually owes us. So we know that we need this much money to get back from the bank. All right, moving on to 12. So for 12, we've got 5,000 frogs in the lake. The population is growing at a rate of 7% per year. We need to find the average rate of change in the population in frogs per year. So average rate of change, this is a little strange because it's just the slope formula. So this is going to be y2 minus y1 over x2 minus x1. So we have to figure out some y's and x's. So we got to find out from year 1 to year 4. But to do that, we actually need to get this equation. So this equation, since we're growing at a rate of 7%, is going to use the other formula. So y equals a times b to the x power. So we're going to get y equals, the number of frogs we start with is 5,000. B, we can see this time we're growing. So if we're growing, we don't want to do 1 minus, we want to do 1 plus. And then our rate here is 7%. So 7%, 7 divided by 100 is 0.07. Looks like I'm getting a little off kilter there. All right, to the x power. So this is the equation that we have to do, and we'll use this to figure out our y values. Now our x values aren't bad because we're going from year 1 to year 4. So we're going to go from year 1 to year 4. So I'm going to do 4 minus 1. You can do 1 minus 4 if you want. You just have to keep the y's consistent. I'm going to do this just to keep all the numbers positive. So I don't really know what I got on top, but I have my equation. So I'm going to put my equation into the calculator. So 5,000, 1 plus, I don't need this 365 anymore. And I'm going to put this in as x. And I want the green, I don't want the blue. Now, again, if I wanted to see this, since it is an exponential, I'm going to go back home and I'm going to come over here to the y. I'm going to put in 10. Don't see anything. 100, don't see anything. 1,000, don't see anything. 10,000, okay, I see my curve. So it's very slightly curved, so this might not be the best, but it's good enough. It's what we want. And in this case, we need to figure out what happens at x equals 1 and at x equals 4. So I got a couple options. First option I can just kind of click on this and try and find out what it is at 1. So it's at 5350, and then at 4, it's a little tough, 6553.98005. So that doesn't seem like I'm going to memorize that, so I feel like that's kind of tough. So option 2, I can type in my two x values that I want. And again, I can just find those intersections. Okay, now I don't need to memorize the numbers. Now I just kind of have the numbers there. So that seems pretty reasonable. That doesn't seem too bad. Option 3 is the option I think is going to be the best, which is if I hit the gear and I make the little table, I can actually just type in what I want. I don't want -2. I don't want 0. I don't want -1. I want 1 and 4. Those are the two that I want. So I think for me, this is going to be the best thing. Now you can do it any of those ways. Oh, I forgot one more thing we could do. Oops. Is we could actually just replace this with a 1 and write down the number. Replace that with a 4 and write down the number. So your choice. You got a lot of choices. But I like this little, whoa, that's not good. I like the little table. So I'm going to sneak my table in here. All right. So with my little table, this tells me the numbers I want to use. So the numbers I want to use are 6, 5, 5. It's a number of frogs, so I'll go 4 minus 5350. So now I have to do this subtraction. So I'm going to go back to the calculator and say, all right, let's do 6554 minus 5350. Get 1204. Divided by 3, because 4 minus 1 is 3. All right, now I got to divide these, and I see right away it's not going to divide nicely. I'm going to get 401 in a decimal, but let's just throw it into double check. So 1204 divided by 3, we get 401.3 repeating. So that's about 401 frogs. Again, as long as we're somewhat close, it's okay to be off by maybe 1 or 2 frogs, just with rounding errors. Again, we have 5,000 frogs. We might not miss one. So we get 401 frogs is our average rate of change. That means we're gaining 401 frogs per year. So this is measured in frogs per year. All right, so we got to do the exact same thing, but now we got to go from 5 to 8. All right, well, that's pretty easy because we can just make this a 5. This is why I like the table. Make this an 8, and I can read those numbers off pretty well. So 8590, 91, it'll round up. 7013, and then 1578 divided by 3. So again, if I'm going to do this, I can go ahead and sneak all of this in here. So I'm just going to paste that all in. So we got all the values. This is the one bad thing about using the calculator is I got to kind of find space for everything. We're going to be able to see everything there. Okay, we will. So again, what I did is I did the average rate of change. And this time I'm going to write down the advanced formula. So change in y over change in x, because my change in y, my y values are changing by 1578. My x's, again, I'm doing 8 minus 5 is 3. If I divide those, then I get 526. So that's what we got. So that's our answer for part B. Again, this is also in frogs per year. And then for part C, we have to find out how much we increase by. So we're going to do 526 minus 401 for 125 frogs per year. And that's how much our rate of change is changing. So that's kind of interesting. We kind of get like an acceleration almost. But we're changing by an extra 125 frogs per year. So again, from year 1 to year 4, we're gaining 401 frogs every year, 5 to 8 on average, 526 per year. So we're gaining more frogs later than we were from years 1 to 4. And that's what we got for that one. So again, it's not too bad. It does use 2 types of formulas though, which is a lot trickier for some people. So we are using our normal y equals a times b to the x formula, and also our slope formula, our average rate of change formula. So we have to kind of combine the 2. So it's all about thinking. The cool thing is if we think about part C though, again, just going back to our graph, if I zoom out, we can see that over here, this is steeper than over here. So that's all part C is really asking, is how much steeper it is. So the important thing is we understand that that is steeper than it is over here. And again, we can even be more extreme and say this is really steep. Over here is not very steep at all. And that's the way that our exponential curves work. Our average rate of changes as we go higher are going to be bigger. That makes these things different than linear equations. All right, on the last one, and this one's just a quick graphing one. So we can see right here, for f, we're going to have an initial value of 100. Again, with our exponentials, we can't really have a linear just counting by ones. So I'm going to start here at 100. We need to decrease at a rate of 10%. So if we were to write that equation out, that would be y equals 100, 1 minus 0.10 to the x. Again, just to be safe, I'm going to graph it in Desmos. So 100 equals 1 minus 10. So now I'm at 100. I'm decreasing, so it's minus, and then 10 to the x. Let's go home. I don't see the graph, so let's change this to 10. Don't see the graph. 100. I see the graph. That seems like that might be pretty good. 1,000 seems too extreme. So 100, maybe we'll zoom out once to make it look a little nicer. Since we want to graph it, I may as well just go ahead and make the table and get all those points and see what points I want to graph. So I got 90 and 81. So over here we got 90 and 81. I feel like maybe we want some more points. Let's get some later points down at the end. So we can keep going. We could do 3, 4, 5, 6, 7, 8. Again, I'll just pull a few of them. 465. Because we can kind of see what the curve is going to look like. We'll pull all the way down at 8 maybe. So it was 8. 43. You can see it's starting to taper off already. Right there. So again, we can see our curve kind of works like this. And here it's going to curve up a little bit. So that's what F looks like. And then for G, we got something very similar. We're going to have an initial value of 80. And we're going to decrease, so minus at a rate of 5%, so 0.05 to the x. So I'm going to do a little dot here at 80. And again, I'm going to just plug it into Desmos. 1 minus 0.05. I need 80. So that's kind of cool because we can see all the dots from the previous curve. So we know that they're going to kind of cross. This one looks like it's going to be a little less steep. But I can delete these dots. Don't really need those right now. I'll get some new dots. And again, maybe I'll get a few more out there. 80, 76. 5 is 61. So 80, 76. And maybe we'll go out to 61. And again, we can kind of see this one kind of goes like this. And that's it. We're just making a rough estimate. It's tough to get a perfect graph with the curves, but that's what they look like. So the important thing is to realize they're not straight lines. That's how they change. All right, so that's everything we got for this one. So there we go.